All right, what's up, everyone? We're back for this new Ecolopto slash Computational Philosophy Research Group Salon. The name just keeps getting on longer. I'll have to shorten it at some point. But I'm super excited to have Professor Josh Bongard today. Many of you probably know him from his work on biologically inspired robots and polycomputation, all of which he will be discussing today. He was also recently on a Foresight stream, I want to say 2 weeks back or so, with Mike Levin, who also many of you will know and are big fans of. And just because we're a little tight on time today, I think we should just get rolling. So Josh, if you want to take it away.
Sure. Thanks very much, Eddie, and thanks for all of you for joining. Yeah, I think this sounds like a really cool group, computational philosophers. I'm in. I'm in. I only dabble in philosophy and specifically in the branch of philosophy that concerns itself with embodiment. What is the role of body in cognition, computation, consciousness, you name it. So I thought what I would do today is talk a little bit about some results that I see as the tip of the iceberg. And what I mean by the tip of the iceberg is when we start to take embodiment seriously, when we consider how the body can compute or cogitate without recourse to brains or neurons or spike trains, that often leads us into interesting territory and challenges us to think increasingly differently about how cognition might actually inhere in organisms and machines. So the thing that I like most about philosophy is it really forces us out of our complacency. What do we assume about, in this case, cognition, computation, and so on? And how might it be different? So I'm going to throw some results at you today, but my main message is um, to show you how embodiment can force us to think differently about computation and cognition. Okay, so as a starting point, not surprisingly, I'm going to start with the xenobots. This is a ongoing joint effort with Mike Levin at Tufts and his group. You're looking at a xenobot here. This is about a millimeter-sized skin organoid. So this is a little organoid made up of about 2,000 frog skin cells. There are no neurons, there is no brain, and yet this simple organoid seems capable of motile behavior. Whether or not it's computing or cogitating remains to be seen. But again, an obvious point to start is with organisms that do not have brains. And I thought, kind of interestingly, today, this is a video of a xenobot, and what we're looking at here are calcium dynamics. These little flashes that you see inside these individual cells are increases in calcium activity within the cell. And today, we published a paper that was co-led by my postdoc, Thomas Varley, and Vaibhav Pai in the Levin lab. And what Pai and Thomas found is that if you take the calcium data from each of these cells and roll out those calcium signals in each cell as a time series, and then compute information metrics on top of them. For example, taking a given cell I and asking whether there's mutual information between that cell I and a cell J, you get something that looks like the following. So in this heat map here, each individual element, ij, reports the amount of mutual information or lack thereof between cells I and J. And if you shuffle the rows and columns, you can find that there are clusters of mutual information. The flashing that you saw in the previous slide is not random. It looks like there are communities within this ball of 2,000 skin cells in which there are interesting flows of information going on. What does interesting mean? Well, interesting in the sense that if you do the same thing with brain data, if you do the same thing with brain data, you take some regions and then look for mutual information between brain regions. You tend to get signatures of information flows that look very, very similar to the xenobots. Just to show you what the null models look like on the right here. So this is if you have a whole bunch of independent signals, there's no appreciable mutual information. It turns out that the similarity in information flows occurring within xenobots using calcium and within brains using electrical conductivity. There are similarities not just between mutual information, but all the other information metrics that neuroscientists tend to study, all the way up to phi, which is often implicated with consciousness. So we are not claiming that xenobots think or are conscious, but there are certainly dynamics going on in aneural tissues that look a lot like the dynamics going on within the nervous system of awake animals. So that suggests that at least computation may be occurring within organisms within the non-neural parts of their bodies and possibly cognition as well. So one of the implications of this work with Mike's group on xenobots led us to do a purely computational study, which is what I'm going to focus on today. And like the xenobot, or inspired by the xenobots here, we're going to do some computation, but we are not going to do it in the normal way. We are not going to use logic gates. We're not going to use simulated neurons. We're not going to use deep neural networks. We're going to do things in a different way. We're going to start by isolating, the atomic building block of computation in all machines, which is the not and gate. I don't think I need to remind anyone here about what that is, but just in case, in a NAND gate, if you supply a 0, 0 at the two inputs, you expect an output, and same with 0, 0, 1. Same thing with 1, 0. And only in the fourth case where you supply 1 and 1 at the two input ports do you expect no output at the output, gate. You can construct arbitrarily complicated, increasingly complicated computers out of just NAND gates. It's a universal building block for computation. Typically, this is done in certain ways, obviously inside of computers that involve electricity in some way. In the work that I'm going to talk about now, we're going to assume that the carrier of information is not electricity, it's mechanical vibration. So what you're looking at
It,
now is a simulated computational granular metamaterial. It's a bit of a mouthful. So let me start with a metamaterial. Metamaterial is made up of a whole bunch of elements that are put together so that the bulk property of the material is quite different from what you would expect from a naturally occurring material. A granular metamaterial is that the little bits that make up the metamaterial are grains. In this case, they're just going to be little circles. So we've got a two-dimensional granular metamaterial. And this granular metamaterial has been designed by an AI to compute. So that gives us computational granular metamaterials, or CGMMs. This particular AI designed CGMM is currently operating as a NAND gate. You can see in this case that we are supplying the 1, 0 case, but we are supplying 1 and 0s as mechanical vibrations rather than electricity. So you can see that the green particle, one of the two input particles, we are vibrating it. That is us supplying a 1. And we are clamping the movement of the blue input particle. We are supplying a 0 at the blue input port. You'll notice that the red particle, which we have arbitrarily designated as the output particle, is vibrating. It's giving us a 1. I won't show you the other ones, but just to paint a picture in your mind, to the right, if we vibrate the green particle and the blue particle, you'll see no vibration at the red particle. If you don't vibrate the green particle and you do vibrate the blue particle, you see vibration at the red particle. And then finally, if you don't vibrate the green and blue particle, you will see the red particle vibrating. So in that way, we can treat this granular metamaterial as a NAND gate. It's vibrating at a certain frequency, 10 hertz here. So at 10 hertz, it's operating as a NAND gate. I mentioned that this is an AI designed granular material. So we've tasked the AI in this case with discovering a material properties of the individual grains. In this very first experiment, we let the AI paint the particles as either stiff or soft particles. Light gray circles are soft particles, dark gray particles are stiff particles. I see there's a question here from Daniel. Is this something like reservoir computing where you choose what output you are listening to? Yes, it's like reservoir computing in that we're going to assume that in a granular metamaterial, there is a reservoir. You can draw out of it dynamics for computation. What I'm going to show you today is that the reservoir goes a lot deeper than at least I thought when we started this experiment. If you traffic in vibration rather than electricity, the reservoir goes a lot deeper than you might imagine. Or do you choose the red particle at the beginning? Yeah, a lot of the design choices here are kind of arbitrary. Good point. Okay, so that's a computational granular metamaterial. The next thing I'm going to show you is what we call, maybe somewhat tongue-in-cheek, a polycomputational granular metamaterial. So polycomputation is this idea that you can design a material to do multiple computations in the same place at the same time without recourse to quantum effects. So I'll just stick with the 1-0 case. Here's the computational metamaterial, and here's the polycomputational metamaterial. Okay, there's a lot going on here, so let me talk about what's going on here. You'll notice there is still the designation of a green and a blue particle. These are the two input particles. So there's still two inputs to this quote unquote gate. And you'll notice there's also a red particle. That's where we're going to observe the result of the computation. We've also added a purple particle, which always vibrates. So we need to apply some constant power, especially for an AND gate in the 0-0 case. So if we want to see a non-zero, output for the 0-0 case, we need to supply some power to this material. So far, so good. If I lost anyone? Okay. All right. In this case, we're supplying 1-0, but we are actually supplying 1-0 twice. We're supplying 1-0 at 10 hertz, and we are also supplying 1-0 at 20 hertz. Again, an arbitrary design decision. So you'll notice, for example, if you look at the green time series, you'll notice that we've just summed these two frequencies. We're vibrating the green particle at 10 and 20 hertz, and we are not vibrating the blue particle at 10 and 20 hertz. So we're supplying 1-0 twice, and we now observe the red particle twice. And this gets back to Daniel's point about reservoir computing. We're going to observe the power of vibration at 10 hertz at the red particle. And if you look at the red time series, you can see that there is power at 10 hertz, telling us that at least for this input case, this material is operating as a NAND gate at that frequency at 10 hertz. And there is also non-trivial vibration at 20 hertz. So this material is also giving us the right answer. It's NANDing the two inputs at 20 hertz. So we are evaluating, or we are making use of this gate, this NAND gate, twice. So it's computing NAND twice for this input case in the same place at the same time, but at different points on the frequency spectrum. That's polycomputation. You'll notice that the particles have different grayscales now. So it's setting this, it's tuning the stiffness of these particles to ensure we get the right answer at 10 hertz and 20 hertz. We optimized this material to have that property, and so we did bi-objective optimization in this case. We want NAND-like behavior at 10 hertz and NAND-like behavior at 20 hertz. Not just at the 1-0 case, but at the other three cases as well. So now you're looking at the 1-1 case. If you look at the green and the blue time series, you'll notice that we're supplying 1-1 at 10 hertz, and we're supplying 1-1 at 20 hertz. And we are getting, if you look at the red time series, we're getting damped behavior at both of those frequencies. There's still a little bit of vibration, but it's very close to zero. So far, so good. It took me a while to wrap my mind around all of this when my PhD student at Tusa Parsa was first showing me. So far, so good. If I lose you at this point, I won't get you back. Okay. All right. So if this is the same material. We're just querying it different times. So you can imagine where this is going. Here's the 0, 1 case. Check. You can still see see significant power at the red particle at 10 and 20 hertz. And then finally, in the 0, 0 case, you can see the purple particle is doing its job here. It's putting some power into this material so that when we supply 0, 0 at 10 hertz and 0, 0 at 20 hertz, we do get an output at 10 and at 20 hertz. So check. You can get AI to design a granular metamaterial that is able to act as a NAND, the same place at the same time at two different points on the frequency spectrum. I would argue that no matter how small you make transistors on a silicon wafer, you cannot put two transistors in the same place at the same time. So this is a horrendously inefficient way to compute, but it does have an advantage over traditional ways of embodying computation in circuitry. Okay. Okay. Comments later about how this relates to informational. Okay. Perceptual cryptography. Love it. That was the original work. Something I want to mention very briefly as a roboticist, we've got to apply this to robotics. So somebody mentioned already the Bratenberg vehicle. If you've never seen a Bratenberg vehicle before, we've got two light sensors on the front, two wheels on the back. We have contralateral connections so that if you come at this Bratenberg vehicle with a flashlight from its front left, more light falls on the left photoreceptor, which causes the right wheel to turn faster than the left wheel, and it'll turn towards the light. We use this to teach undergraduates about robotics all the time. This is a light. What happens if we change to vibration? So imagine we have a robot operating in a vibrational environment in which there's a stronger vibration on the left than the right. It's not too far a jump to imagine vibrotaxis, a robot that's able to turn towards greater power of vibration. You could do it by having a robot with wheels, or you could replace the wheels with something else that vibrates so that the thing that vibrates at the back right causes the robot to turn to the left. We're gradually replacing all the parts of a robot, sensors, motors, with vibration. Finally, we could get rid of the wires altogether. You can imagine a robot made from a granular metamaterial where the external vibrations supply information and power if these are mechanical vibrations. Yeah. So if you design this metamaterial correctly, there should be a propagation of these external vibrations through the body of the Bratenberg vehicle so that there's more vibration arriving at the back right, causing it to turn. And this is something we're working on. We haven't realized it yet, but if we do, you have a machine that completely conflates quote unquote thought and action. In a simple Bratenberg vehicle, there's the body, there's the chassis and the rubber of the wheels, for example, and there's the brain, there's the wires, and maybe you include sensors in body and brain. There's still this Cartesian cut. But in this route, we can go where there is no longer this Cartesian cut. There is no distinction between thought and action, or computation and action, if you like. Okay.
I want to make. I'm going to make one slight pause on that kind of phenomena.
Sure.
There are really interesting states of. Let's not use the word consciousness. We'll say states of perception-like activities, and these very deep states of say meditation. So we're actually going to be having a guest in a couple weeks. Has this active inference theory of consciousness and perception, and there's this phenomena called Josh. I don't know if you've heard of the cessation, like cessation of consciousness is sort of the idea, and it's that you can basically, in a weird way, almost experience something that's not experienced, and that like it's basically that you're no longer your thoughts and your perception and everything kind of just mix into one. And so there's no way to tell the difference between them. Is that sort of what you're kind of getting at?
Yeah, anything that conflates things that we tend to assume are distinct components of cognition or consciousness, I would say is in
Right.
the right spirit. Absolutely.
Just a
Yeah,
quick
very cool.
comment on that. Actually, you don't have thoughts or action in cessation. So that question wouldn't apply.
Interesting. Okay, good to know. Thank you. Well, yeah,
Great.
yeah. So it's that everything sort of seizes, right? Okay. All right. We have to continue this. Yes. Sorry. Go ahead,
Okay.
Josh.
Interesting. Interesting. Okay, I've got 20 minutes left, and then I would prefer to just have a discussion. So let me take you another step deeper down the rabbit hole. Here we go. Okay, this is some more recent work by my postdoc, Sean Bolio, and he started out the same way. He created, he's optimizing the properties of grains of a granular metamaterial so that that granular metamaterial exhibits a certain bulk property. And that bulk property, again, is going to be computation in the traditional Boolean sense of NAND gates and OR gates and AND gates. So same setup. The only difference is going to be the loss function. As you're going to see in a moment, Sean is going to challenge the machine learning algorithm to come up to basically discover a material that can do has a greater density of computation than the material you just saw. Here we go. You're going to I'm going to just show you this abstract figure, and at each point, we're going to assume there is a material that has been optimized to do the following. And Sean actually did this. I don't have time to go into the details. Okay, step one, Sean takes a given frequency, which we'll denote as omega 0, and at frequency omega 0, he simulates a granular metamaterial and supplies 1, 0 as the input, as you can see here in the box. And the 1, 0 is written in bold font. Bold represents that the output is 1. So this little purple box here is telling you that Sean optimized a granular metamaterial so that if you vibrate the left input particle and don't vibrate the right particle, 1, 0, you get vibration at the chosen output particle. He kept going and said, and also, if when you simulate this same material another time and you supply 1, 1 at the two input ports, you should expect, or you should get 0 at the output. You'll notice that the 1, 1 here are not in bold. He managed to optimize a material that does that. If you supply 1, 0, you get an output. If you input 1, 1, you don't get an output at omega 0. Again, we're computing with vibration here. Okay, 2 more cases. If you supply 0, 1, you should get an output. And if you supply 0, 0, you should get an output. If the AI designs a material that does all of these 4 things, you have a material that acts like a NAND gate, as you just saw. So actually, this is nothing different from Atusa's material that I just showed you on the previous slide. So far, so good? Okay. However, Sean kept going. He then asked at a separate frequency, omega sub 1, if you supply 0, 1, at the same time that you supply 1, 0 at omega 0, you should get no output at omega 1. You'll notice that O1 is not in bold. This is something that he asked the machine learning algorithm to optimize into the material. So you'll notice there's 5 boxes here. So at this point, there's 5 components in the loss function, and Sean successfully got a granular metamaterial that does all of these things. You can maybe guess where we're going with this. He added 3 more terms to the loss function. So now we have a loss function with 8 terms. The machine learning algorithm returned a metamaterial to us that has these 8 properties. It can do all of these things. So you'll notice that at omega sub 1, at that frequency, the output particle only vibrates when you supply 1 at both input gates. You'll notice the 1, 1 is in bold. So now he's optimized a material that computes NAND at omega 0 and computes AND at omega 1. Seems like kind of an arbitrary choice. You'll have to bear with me for a moment. Okay. He added a third frequency. So now in the first simulation, in S0, he supplies 1, 0 at omega 0. He supplies 0, 1 at omega 1 and supplies 0, 0 at omega 2. And he's looking, or the machine learning algorithm is looking to see that there is an output of 1 at omega 0, an output of 0 at omega 1, and an output of 1 at omega 2. I know that it's kind of a lot to hold in your head at once. So he's managed now to pack 3 gates, 3 different gates into a single material, and it's able to embody all 3 gates as long as you supply these input cases in the right combination. So for example, if we look at the leftmost column, you always have to put 1, 0 in at omega 0 and 0, 1 at omega 1 and 0, 0 at omega 2. So there's a catch. You have to do it in the right way. They're not all independent. Okay. He kept going. At omega 3, if you supply the inputs at omega 3 along with those other inputs at those other frequencies, the machine learning algorithm is able to give you back or at the 4th frequency. So now we have one material that's computing 4 different gates simultaneously at 4 different frequencies. So far, so good? Okay, now I want you to look not at the rows, but at the columns. And you'll notice that the order in which we supply these inputs was not arbitrary. If you look inside of these 16 boxes, you'll notice that this is a Latin square. So on every row and column, there is the full set of these 4 cases, which means that if you read down the column, you'll notice that at the 4 frequencies, we are actually, at each of the 4 frequencies during that simulation, like S0, at those 4 frequencies, we're supplying 1 of each of the 4 input cases. If you count from the top to the bottom of the column, we supply 1, 0, then 0, 1, 0, 0, and 1, 1. And we already know what the outputs are. The outputs are 1 at omega 0, 0 at omega 1, 1 at omega 2, and 1 at omega 3. So it turns out that if you read down the column, you're also getting a 5th gate. You're getting a 5th logical operation if you look across frequencies during the same simulation. And that logical operation is material implication, which can be written as not B or A. So it's an actual recognizable logical operation on 2 binary gates. So when we look across the rows, if we're looking across the simulations, we get a complete gate at individual frequencies. We also get an individual and complete gate or operation if we look across frequencies during the same simulation. So far, so good? Okay. Okay, we can keep going. It turns out that if you look at simulation, the second simulation, S1, in that case, during that simulation, the input gates were agitated in the way that you see here. And again, we've supplied all 4 input cases. And if we look across those four frequencies, at the 4th frequency, omega 3, it only lights up there. And that is material non-implication, which can be written as A and not B, where A is the left input and B is the right input. So this comes back to Daniel's point about reservoir computing. So what we're actually doing is stacking observers. We are observing this material from different quote unquote angles or different perspectives. And when we do, and if we get more and more recognizable Boolean operations being performed, or at least embodied in this material, but we only get it if 2 things happen. You've got to create a Latin square of these input cases, and you have to design the metamaterial to do that. You can't randomly put together a bunch of grains into a metamaterial and observe it from different perspectives and see recognizable gates. You typically get things that aren't logical operations. The output gate is always on, the output gate is always off, or the value arriving at the output is not a reliable, it does not reliably follow from the agitation of the inputs. There's lots of things that can go wrong. And if I had more time, I'd go into it. I knew somebody was going to ask me this question. What happens if you go beyond 4x4? I'll get to that in a moment. So I think you get the game we're trying to play here, which is how do you structure the way in which you query the material, and how do you design the material to pack more and more recognizable logical operations into the same place at the same time. It took Sean a while to figure out this Latin square and get the machine learning algorithm to cooperate. But when he did, in the third simulation, it also produces which one is this? Material non-implication, but with the other two gates, and material implication, but the other way around, swapping the two gates. So in all 8 cases, you get a recognizable Boolean operation. And this is the point where I always feel like a car salesman. And that's not all. There's more. Some of you who had your caffeine this afternoon, you might see that there are 2 additional gates buried in this material. You can extract 2 more. Angles, yes. So if you look along the main diagonal, if you march from top left to bottom right, you have exclusive OR. Again, because it's a Latin square on the diagonal, you get across frequencies and now also across simulation. So you get the computations in the same place, but not at the same time. Okay, yeah, XOR is the best one. Agreed. You can probably see where the 10th and final one is, which is along the other diagonal. So as you march from bottom left to upper right, you also have exclusive NOR, not OR. Okay. So what happens if you do 5x5? It's problematic because you no longer have a Latin square. It's impossible. We're dealing with two binary input operations. So it breaks the requirement of a Latin square. You start to get redundancy. But my postdoc, Sean, I believe, showed that even with redundancy, you can get recognizable gates along all the columns and all the rows and the 2 diagonals. Okay, 8x8. Oh my goodness, it's a good question. Okay, I will pause for a moment for questions before finishing off
Perfect.
my exposition.
Cool,
here.
cool, cool. All right, so you got like what, 20 minutes or so, right?
Yep. Sorry, just the last thing I want to mention before we go fully into the Q&A point. One other observation to make before we leave this set of results is in this work, you only get all 10 gates when, for example, during one simulation, you supply 1, 0 at omega 0, then 0, 1. So they seem to be coupled. So if you take the leftmost column, and you take this optimized metamaterial and you supply 1, 0 at omega 0, but then you don't supply 0, 1 at omega 1, you supply one of the other 3 input cases, it's not guaranteed that you're going to still retain all of these 10 gates. I have a very talented PhD student, Piper Welch, who's looking into the logical independence of these polycomputational materials. Can you, for example, train the material or design the material according to this setup, but then start to supply different input cases at novel combinations of input cases and input frequencies, and not disrupt the polycomputational potential of the material? Piper has shown that yes, you can get ML designed metamaterials that are logically independent, but we don't know whether they're logically independent enough for situations like this. Okay, so just a couple of concluding remarks. Interestingly, in last year, it was discovered, let's see, it was discovered that neurons actually mix also mechanical vibrations. And so I don't know whether neurons are doing what I just showed you, but I think, at least for me, one of the takeaways as a roboticist and somebody interested in embodied cognition is that we should not assume we know how computation is performed in the brain or anywhere else in the body. However, computation and cognition actually is performed in the body and brain, it's probably way, way stranger than things that we can think up. So that takes us back to my iceberg. So I've shown you the tip of the iceberg here, but the iceberg I hope for you to take away, and I'm sure you know this already, but truth is probably going to be way, way stranger than we think. The back propagation of error, super useful, obviously, but it's probably not the whole story. Okay. All of the folks on this slide helped with this work in one way or another. Work was sponsored by NSF, DARPA, and some money from UVM and Tufts. Okay, thanks. Looking forward to a bit of a discussion.
Wonderful. Thank you so much, Josh. This was great. I have many questions and thoughts, as I'm sure some people here already know. I'm going to try to keep it at a minimum. Many thoughts on how coordination relates to computation. I have this thing I talk about a lot that everyone here has heard a million times. Computers are magic rocks. At least modern computers are magic rocks, and that we found a way to have this sort of mass coordination of specific physical, materials and substrates to create this thing called a computer that we're all talking on right now, right? So the elements of these things exist distributed throughout, say, the planet. And then there's some kind of coordination process that's able to bring it together. And in a sense, collectively, you can enhance, let's say, the intelligence of these rocks by turning them into machine learning systems and all that. And in a weird way, I like to say that they're like learning rocks, right? And I've many questions on your evolutionary computation ideas about how nature could have evolved its own kind of let's say silicon-based computers without the help of humans. What other ways would, through through certain kind of crystals and mineral processes, how they would have created something computational. But what I wanted to actually follow up on was a comment I said earlier about perceptual cryptography. So in my head, the general idea of like what cryptography is that you're sending out some kind of signal, some kind of information, and it's going to look two different ways to different observers. All right. So one of the ways that people will send out a signal is that they'll hide it in plain sight so that only the right observer is going to be able to pick up on it. And one of the most fascinating, perspectives on this is have you seen or have you heard the what is it, the green needle brainstorm audio illusion? Have you heard that one before, Josh? So
Nope.
it's based off of this cartoon from the 2000s called Ben 10. There's this fancy watch that lets the guy turn into aliens, and it's the toy of that cartoon. And if you play the sound on one side, it sounds like it's saying brainstorm, and then the other sounds like it's saying green needle, even though, as far as I'm aware, the actual audio is sort of technically staying the same, and it's only the observers, the cognitive aspect, that is literally picking up two very different forms of information from that same kind of signal. And that sort of relates to that idea of informational ambiguity as well, where like the letters that we have on our screen right now are just squiggles, right? If I only knew Japanese or something or Chinese and I saw these English letters, I wouldn't really be able to make sense of it. It's only to the right observer that these things even make sense. And I think perspective on what you're getting at with polycomputation and all of your ideas is that these different materials are like different agents, and they have different ways of interpreting the information around them, which gives them potentially different behaviors, you could say.
Agreed. Absolutely. It's the packing of observers
Right.
that's the key, right? And this is something that
Yeah.
I think reservoir computing started to pick up on. So if Mother Nature made a computer, it's not necessarily the focus on, the computational structure that would be of interest. It's the ingenious ways in which she figures out how to pack, to maximize the density of observers across all physical phenomena, across the frequency spectrum, across spatial and temporal scales. That's what she's very good at. And I think that we've just started to play that game.
Cool. I want to take, since we're low on time, does anybody else have any other questions for Josh? I think there's a couple people. feel free to just, oh, Dan, go for it.
Yeah, this is so fascinating. I ended up switching because of some logistical issues, but I was originally going to do my dissertation on evolving materials for polycomputation and reservoir computing. So
Cool.
this is very, very, very exciting. I'm curious, is do you only see this kind of computation and granular metamaterials? Did you try a few things and this is the one that worked, or is this the only one that you've tried and you think there might be other kinds of things that you can do this with?
The latter. We've only tried with granular metamaterials because, as you can see, oh gosh, I didn't include her. I feel bad. Rebecca Kramer-Botiglio at Yale, she runs the Fabratory, and Corey O'Hearn, also at Yale. They were collaborators on this work. I've got the wrong collaborator slide up here. My apologies to my collaborators. Rebecca's group is really good at making granular metamaterials, so we're focusing on granular metamaterials. We've got some work on trying to cross the sim to real gap to embody these simulated materials in reality. I will say it's possible, but stay tuned. But yeah, of course, why wouldn't another metamaterial or something that isn't even a metamaterial? Mike is very excited about looking for polycomputation in natural materials. Why wouldn't they simultaneously compute across the frequency spectrum or the electromagnetic spectrum if they could?
And then if I could ask a quick question and then I'll step out of the way. Um, do you see, so obviously if you everything's a simulation, it's really easy to kind of evolve your metamaterial to get the desired behavior.
It's
Um,
not definitely not easy. It's possible, or else I wouldn't be talking about it, but not easy.
so it's possible if everything is in silico to kind of evolve your metamaterial. Do you see it if your collaborator has this lab with granular metamaterials? Do you see it as being equally possible to kind of evolve the physical material? So you're doing everything sort of out of simulation.
Yeah, good question. I don't. I'm going to answer your question vaguely, just because the work hasn't been published yet. But Rebecca's group has been making great progress on making grains that have tunable properties. So
Wow.
easily tunable properties, and then the idea would be obviously how intuitive is that process? Through human intuition, can you tune the properties of grains to get, a non-computational bulk property of interest? And then obviously the connection to this work is the AI just dictates the settings for the material properties of the grains.
That's fascinating. I'm definitely going to be keeping an eye out for that as soon as it's out.
Great. I'll just type Rebecca's name here into chat for those that don't know it.
In the meantime, Damaris, did you have a question? Or Jess, or go for it.
Yeah, thank you. I had the 4x4 question that I guess
Okay.
you're getting all the time. So I mean I can guess the answer, but I'd love to hear your take on that. But and also maybe a more philosophical one is in other approaches to mind body, like let's say active inference, we already have kind of more or less an inflation, like a collapse of mind and body into one system, in one computational system. And so I'm kind of wondering, like, how does your approach maybe add something to that debate? Like, because it's a
Yep.
very different angle, obviously.
Yeah, good question. So I would say that you're right. Active inference, and some other branches of inquiry have argued that you can conflate thought and action. You can conflate mind and body. The assumption, as far as I know from reading the literature, is yes, either you can or you can't. But if you view this through a polycomputational lens, you could imagine an agent in which at one frequency, mind and body are actually quite separate, but at a different frequency, they're conflated. So, coming to the conclusion that there is conflation or there isn't, or there's this amount of conflation or the conflation is of this nature, you can't categorically conclude that because there may be other things going on across different physical modalities or different points on the electromagnetic spectrum. So maybe there's a conflation of thought and action in terms of mechanical vibration, but optically there isn't. And, electrically there is, but only to this amount. So I think we can revisit those questions through this polycomputational lens and ask what is occurring at the same place and possibly at the same time within an agent, but at different points within different physical phenomena.
Awesome.
And if you think about it from an evolutionary point of view, why wouldn't it be? It would be very inefficient if the same thing was happening on all different modalities at all different size and temporal scales. My guess would be probably not, but it remains to be seen.
Cool. All right. I know you got to get going soon. Does anybody else have one more question for Josh?
I guess just a brief follow-up on that very quickly, just asserting, reaffirming things, but like, yeah, biologically speaking, if you're combating against all the pressures of survival, having something that's like contingent or resonance based or agreement based on the frequencies, sort of determining on the need versus a lot of the things that we look at a set structure, looking back, trying to like reduce it or trying to deal with the complexity, or excuse me, looking at things as a fixed sort of a fixed structure that we're trying to analyze versus the ground up, it will be done contingently, I think is a really interesting like philosophical bent to this. And I think we're trying to I think we're getting at very interesting, like polycomputation is a very interesting lens to look at that in. So I'm curious where we go with that.
Agreed. Yeah. Lots of work to be done there.
So I actually want to follow up on the cessation thing and get Damaris involved in that for a moment about Damaris, how are you defining cessation? It's sort of the absence of thought.
So I've never experienced it, but from the literature, especially if you look at the Buddhist literature on jhanas, that would come at a point when all types of what we would consider perception ceases. That's where the word cessation comes from. So you don't even have like the perception of infinity, like, infinite consciousness that is very typical, nor do you have then the perception, the realization there's nothing within that infinite consciousness, which is the next jhana afterwards. So there's still like a sense of something, of like a nothingness. But even that then, so you don't have a subject-object split anyway in these deeper jhanas, but also at that point you actually lose every type of perception, which is why usually the state is called neither perception nor perception. Like none of our typical inquiries apply. So thought in the sense doesn't exist, as perception in general doesn't seem to exist.
I mean, for me, and reading, what people like Ruben Lauconen would talk about this, is that to me it read like it's a sort of a hibernation state, like a cognitive hibernation in some weird sort of sense. And then I wonder, like from a computational perspective, what is cessation? What are the absence of these things that we call thoughts? And then, you could also say, what do we mean when we talk about thoughts and perception and all that? But this is sort of a question for Josh as well about, like, from a computational perspective, what does it mean when you have the absence of thought?
Well,
Oh gosh.
That's a very philosophical question.
Or how is it just different from so much noise that there's no signal to be determined?
Right.
It depends on, like, okay, what thought are you talking about? Like, are we talking about like the inner narrator or the inner pictures? Because they already disappear in the early jhanas. Then if you come to infinite consciousness, right, already at that point, you don't even have emotions anymore. So even if you think embodied thoughts in that sense of like emotions or sensations or feelings, all of that is gone, right? No coldness, no warmth, like none of that. So like it depends, like what do you define as thought? Like, and then like each jhana has a different versions of like a mental phenomena that kind of goes offline.
Yeah, and it's weird that you can maybe see these phenomena, and let's just say man-made computational systems. So in different kinds of let's say bio-inspired systems that we can make. I mean, what would be really interesting is that what are the benefits to having that mode of existence, of experiencing in a weird way, even though you're sort of not experiencing? Like, what are the benefits? Because I've heard a lot of people say that it's sort of like you're refreshing things. I mean the example that I give for stuff like this, and this is also a question for Josh really quickly because he's got to go. I always think about biological systems seem interesting compared to the way that we'll typically engineer machines, right? Or at least maybe not as much modern learning systems, but let's just say something like a car. Like if you have an engine that's running, good luck trying to fix the engine while it's running. You have to shut it off. You have to temporarily suspend its entire state of dynamics and everything. You have to sort of freeze it for a bit, and then you'll go and diagnose what the problem is or whatever and try to change out whatever parts. But you can't actually change that while it's running, right? At least most parts, you can't do that. Now, in biological systems, it seems that you can have the thing running and still change its components while it's running, right? Which is interesting that there seems to be a almost a sharp difference there. Curious if any thoughts on that, Josh.
You know, it's tricky, right? Because the metaphor to the car, you're tying it back
Right.
to action.
Right.
You know, cards on the table, I'm an illusionist. So, you know, I don't know whether thoughts are
Yeah.
actually a thing. What I
Right.
would say is when you enter into metacognition, when you cogitate on your own cognition, right? There seems to be, it feels like, you know, there's an observer, you, that's observing something inside. I feel hungry, so I'm thinking about being hungry and going to do something. There's an observer who talks about what the observer thinks they are observing. And sometimes that narrative, those words line up with the actions that this thing does at a short time into the future, which is go get a sandwich. So, you know, to me as an illusionist, that's the closest you can get to defining what a thought is. It's something that an observer thinks they observe introspectively, and it matches up to external behavior at some point. Now, whether there was actually anything to observe during that process of metacognition or not, as an illusionist, I don't know that there's actually anything there, or whether that's subject to scientific experimentation. It feels, you know, coterminous with qualia, but there you go. I mean, so, but if you have multiple observers in a polycomputational lens, you might have multiple observers entering into metacognition and narrating what they think they see inside at different frequencies or according to different physical phenomenon. And those verbal reports occurring at different frequencies match up with different behaviors or actions or phenomena occurring in future at those frequencies. So maybe polymeta computation will be a thing someday.
Sounds like
Polymeta
multiple
computation.
personality disorder.
Yes,
Polymeta.
yeah, exactly, right? We think we're I's, but we're really we's, and most of the time we're good at convincing ourselves that we are not a plurality, right? And sometimes that illusion breaks down. Yeah,
Right.
agreed.
Interesting.
Poly-
Okay.
There it
All right.
is.
All right. I know Josh
Polymeta
has got to go.
computation as a phenomenological rigor aid. So
We
we'll
got the
see.
title of the paper already. All right,
There
write
it is.
down all the co-authors here before we all leave. Love it,
There you
Jess.
go.
Great.
Good stuff. All right. Thank you so much, Josh, for your brilliant
Thank
presentation.
you all.
Questions
Thank
from
Super
us.
fun. Thank you. Sounds
Thank
great.
you,
Thanks,
Josh.
everyone.
Where
Thank you,
can people
Josh.
find you online, by the way?
Oh, you just Google my name. I'm everywhere.
Cool.
Okay.
All right. Perfect. All right. Thank you, Josh. You take care.
Bye.